everyone, I'm teacher Angeline and today we are going to learn about the concept of movements of substances across a plasma membrane.
Hello, I'm Jack Sparrow. I'm also a student here.
So in this topic, we will learn three important things, which is the first one is the characteristics that are able to move across the plasma membrane, the examples of the movements of the substances, which is the passive transport and active transport, and the last one is to compare and contrast between these two transports. Do you know that not all molecules can pass through plasma membranes?
I'm not sure, teacher. Will you explain it for us?
Sure, Jack. There are a few common factors that can determine whether a molecule can pass through a plasma membrane or not, which is the molecule size, molecule polar, and the ionic charge. This is why only certain molecules can pass through these plasma membranes. The substances can be divided into two, which is the lipid-soluble substances and lipid-insoluble substances. So under these lipid-soluble substances, we have non-polar molecules. So in lipid-soluble substances, we have non-polar molecules such as fatty acid, glycerol, fat-soluble vitamins, and steroid compounds. As for lipid-insoluble substances, we have small molecule, which is polar molecule. So Jack, can you give us the examples of these polar molecules?
Ooh, water!
Very good. And we also have non-polar molecules such as
Oxygen and carbon dioxide.
Yes, thank you. Not only small molecules, we also have large molecules under the lipid-insoluble molecules. Jack, can you give us the examples?
Glucose and amino acid.
Impressive, Jack. Let's learn about passive transport. To easily understand this passive transport, you just need to imagine that you are riding a bicycle downhill. Logically, we don't need any energy as we go downhill by using the bicycles effortlessly. So this concept same goes to the passive transport. You don't need any energy to do this process. Yes. So there are three examples that we need to know in passive transport, which is simple diffusion, osmosis, and facilitated diffusion.
I cannot imagine them. Can we just travel into it or something?
Well, that is possible. Let's go!
OMG, my new home!
This is not the sea, Jack. This is the animations of simple diffusion.
Cool!
Simple diffusion is the movement of molecules or ions from an area of high concentration to lower concentration. Follow the concentration gradient until a dynamic equilibrium is achieved. This may happen with or without the presence of a plasma membrane.
So let's move to the next passive transport, which is osmosis.
Whoa, I love water.
Osmosis only involves water molecules. Osmosis can be defined as a net movement of water molecules from an area of high water potential, which is low solids concentrations, to a lower water potential, which means high solids concentrations randomly from selectively permeable membrane.
Wait, what does it mean by low solids concentration and high water potential?
That's a good question, Jack. High water potential means there are greater number of water molecules. So, the solids concentrations is low because...
Oh, it is because as solutions become more concentrated, there are less water compound in it?
Yes, correct.
But teacher, how about those molecules that cannot enter the plasma membrane through simple diffusion and osmosis? We cannot leave them behind.
Well, of course they can, but by using the facilitated diffusion.
What is that?
This is the facilitated diffusions and the huge thing in the middle called channel protein, or we can say it as carrier protein. So for lipid-insoluble substances such as large molecule or ions, for example, glucose or amino acids. So for those lipid-insoluble substances such as ions and large molecules such as amino acids and glucose that cannot pass through these plasma membranes, this carrier protein will help them to get through. For your information, this facilitated diffusion is similar to simple diffusions as it does not require any energy. This protein here helps to transport molecules down the concentration gradient until this process achieves a dynamic equilibrium.
I see. Let me see if I can pass through the protein.
Jack, there is something that you need to know about this carrier protein here. This carrier protein has a specific sites where it can bind to specific molecules. So once it binds, this carrier protein can change its shape and allow some substances, specific substances or molecules, to get passed through it.
So once the channel protein changes its shape, I can still enter, right?
No, I'm afraid that you cannot, because carrier protein can return to its original shape and get ready to transport other molecules. Not you, Jack. You are not specific molecules. You are a cat. I'm sorry.
Okay, fine. I do not like this facilitated diffusion.
Okay, finally, let's move to the active transport. Active transport. Active transport is very much different from passive transport. It is because this active transport molecules or ions from an area of lower concentrations to a higher concentrations, which mean against the concentrations gradient. Jack, do you remember the bicycles concept from the passive transport?
Yes, simple passive transport has the same concept as riding a bicycle downhill, as there is no energy needed.
Yes, and it worked reversely for active transport, where we need energy from the ATP. Means, now for the bicycle concept, we need to ride the bicycle uphill, which means against the concentration gradient, and we sure need a lot of energy to do so. Here, the carrier protein has the same functions as in the passive transport. But differently, in active transport, we call this carrier protein as a pump. The most common examples are the proton pump and the sodium-potassium pump. But now, let's focus on the sodium-potassium pump first. So, here's the general process.
It involves the binding of ATP to the pump, which promotes the binding of 3 sodium ions and the release of 2 potassium ions. Here, ATP is broken down and decomposed into ADP and phosphate, then bound to the pump. The pump then changes its shape, and 3 sodium ions is transported out of the cell through the carrier protein. At the same time, the pump binds to potassium ions, and the phosphate group leaves the carrier protein. Due to the loss of the phosphate group, the pump returns to its original shape. So, the 2 potassium ions can be transported into the cell, and the cycle begins again.
But how about the proton pump?
Proton pumps involve hydrogen ions, where it still has the same concept as sodium-potassium pump, where we still have to use energy from ATP to transport these hydrogen ions out of the cells by using the carrier proteins.
Oh, there are many processes to be processed here.
Indeed, Jack. So before we end these lessons, let's compare and contrast the passive transport and active transport. We already know that both passive and active transport move molecules or substances across plasma membrane and occurs through a selectively permeable membrane. But to contrast, passive transport here does not require any energy as it follows the concentration gradient, while as for the active transport, we need energy because we go against the concentration gradients. Not only that, the transportation process in passive transport occurs until it achieves a dynamic equilibrium. Okay, and as for the active transport, we need to have these accumulations and disposals of molecules or ions in the middle of the transportation process. So that's all from us. Thank you for watching. Bye!